Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the logarithm function. Last time we saw some properties of the exponential function. One of the properties was that it converts addition into multiplication. So this is what it says. And we saw that the exponential function is a bijection, amongst other things. Alright, and before we move on, let me just give you a little exercise which we have done before. So start with a differentiable function, domain being these positive reals and the reals. Assume its derivative vanishes everywhere. And assume that it takes the value 0 at some point, let's say 1. So then you can show that the function vanishes everywhere. And one way to do this is the mean value theorem. You can do it in other ways. Alright, so we saw that the exponential map is a bijection, and therefore it makes sense to define the inverse of this. Or rather consider the inverse of this, and the inverse of this function is what we call the natural logarithm. I will not be using the phrase natural, or rather the word natural. I'll just call it logarithm so that it's for the sake of brevity basically. So the notation for this is log. Many times you will see ln, but I will just stick with log. Great. And now since this is a differentiable function, the exponential function being a differentiable function, and its derivative does not vanish anywhere because its derivative is itself and the exponential function does not vanish anywhere. We see by the inverse function theorem that the logarithm function also is differentiable. So we see by the inverse function theorem that the logarithm function is differentiable and the derivative of the log can be calculated in this fashion. So let me explain that a little bit. So what we have is log composed with the exponential is the identity. So by chain rule, if we take the derivative of the left hand side at x, we see log prime x of x times x prime x is 1 because the derivative of the identity at any point is 1. So this gives us log prime e to the x is 1 upon e to the x. But what this really is saying is that log prime of x is 1 by x for all positive x. That's what really is being said here, because every real number can be written in the form e to the something. So this is a very simple fact, and since we can calculate the first derivative of log in this very nice way, we can calculate all derivatives. Alright, so let's see one more small fact which is a consequence of the above. So we want to show that log t is this integral. Alright, so define a function from positive reals to reals as f of t is integral 1 to t 1 upon x dx. Okay, so we have defined something. By the fundamental theorem of calculus, we have that f prime t is 1 upon t, and clearly f of 1 is 0. Because f of 1 is the integral of 1 upon x from 1 to 1, so it's 0. But 1 upon t is also the derivative of log at t, as we just saw, and 0 is also the value of log at 1. Why is that? Because log of 1 is nothing but log of exp of 0. Exp of 0 is 1 by definition of exp. So since log is inverse of exponential, we see that log of 1 is 0. Great. So what we see is that if we define g from positive reals to reals as g is f minus log, we see that g prime is 0 everywhere and g of 1 is 0. G prime is 0 because g prime is f prime minus log prime, but f prime and log prime are the same functions. And g1 is 0 because f1 and log1 are the same values. So this is what we recalled in the beginning of this lecture, that this implies that g is 0 everywhere. Thus g is the 0 function, and hence f equals log, which means that this is the fact, and we've proven it. Great. Now it's a little bit, well, so I want to give you an exercise, but I will give some details. So we want to consider the Taylor expansion of the logarithmic function. We see that it is differentiable as many times as you want, because its first derivative is 1 upon x, and 1 upon x is differentiable as many times as you want on positive reals. So log is a as many times as you want differentiable function, and so we can take its Taylor expansion up to some k steps and take the remainder part. K could be any positive integer, and this is the general formula for Taylor expansion of a ck plus 1 function, where this thing that you see here is a real number strictly between a and a plus h. Okay, so if you do that, you will see that log of 1 plus x for x for mod x less than 1, it does not make sense to consider mod x greater than 1, because log of 0 is not defined. You can't have x equals even minus 1, so you're only allowed to take values here when you're doing the Taylor expansion. So log of 1 plus x is the polynomial part and the remainder part, and the polynomial part will look this way because you can just calculate the derivatives of the log function very easily. So this is how if you calculate the polynomial part will look like. And now one may guess that maybe this is the power series for log x. Just like for exponential function is given by a power series, perhaps log function is also given by a power series. So let's see if the corresponding power series, the power series that is motivated by this expression converges or not. So indeed, if you look at this power series, this converges because of a ratio test. You can easily do that. And you can also show that the remainder term goes to 0 as k goes to infinity. So again, this is a little bit of an exercise, but you can then show that for mod x less than 1, log of 1 plus x is actually given by this power series. So just a small fact, it's pretty useful at times. Okay, fine. Let us look at two simple properties of log, or rather just one simple property. So log, we want to say that log of x plus y, log of x times y is log x plus log y for all x and y. So why is that? So let x equals e to the a, or let me write x of a, and y equals x of b. Why can we find such a and b? Because exponential function is a bijection. In particular, it's a surjection from reals to positive reals. So if you pick two positive reals x and y, there exists some real numbers a and b such that this happens. Okay, so thus log of xy is log of x of a times x of b, which is log of x of a plus b, which is a plus b, which is log x plus log y, because if you take the log of both sides here, you will see that log x is a and you'll see that log y is b. So that's why we are having this, and that's it. That proves our lemma. And a simple corollary of that lemma is that if you have any natural number n, then log of x to the n is n times log of x. So x to the n is just x times x times x n times, and if you apply the above repeatedly, you'll get that. Okay, great. And now let me just take a simple example. This is a very famous limit, useful at many instances. So I want to show that limit n going to infinity of this guy is actually x of 1, which we denote by just simply e. This number x of 1 is denoted as e. So let me prove this. So let an equals this nth term and define bn as log of an. Okay. So thus bn is n times log of 1 plus 1 by n. Alright. So now here I will use the Taylor expansion. This is n times. So I'll take Taylor expansion about 1. Let me tell you exactly what I'm doing. So here you take a equals 1 and h equals 1 by n in this expression, and I will use k equals 2. So if you do that, what you're going to get is, well, I'll also have to calculate, but you're going to get this. Let me make this calculation quickly in my rough notes and get back to you. Yeah, so you will get 1 upon n minus half 1 upon n square plus 1 upon 3 1 upon n cube into 1 upon n 1 plus, yeah, so this is something strictly between 1 and 1 plus 1 by n. So this will be I think this will be the derivative of log at something between, yeah, so this will be something like 2 plus lambda by n, where lambda is strictly between 0 and 1. For some lambda is strictly between 0 and 1. So yeah, you have to verify this. So this is the remainder term of the polynomial of the Taylor expansion, r2x or r2 1 by n, and this is the polynomial term p2 1 by n. Great. So yeah, you should also calculate this because I may have made a mistake, but anyway, I have not made a mistake here, I'm pretty sure. So this is equal to 1 minus 1 upon 2n plus 1 upon 3n square to this horrible thing, and this horrible thing is 2n plus lambda whole cube. So therefore limit n going to infinity bn is 1, because these things are dying down to 0. So we get 1, and this implies x of limit n going to infinity bn is x of 1, which we write as e. But since x is a continuous function in particular, we can kind of pull out the limit. So we get limit n going to infinity x bn equals e. But by definition, this is just an, because x of bn, if you look at this equation, x of bn is x of log of an, but x of log of anything is the anything. So we get that. This is a very commonly used limit. Let me give an exercise here. So exercise, show that limit n going to infinity 1 minus 1 by n to the power n is 1 by e. It's a very similar calculation. Okay, so let me end this lecture with the general notion of exponent. So fix a positive real number, and then for any real number alpha, we define this symbol as this expression. And this may seem like it comes out of nowhere, but the motivation is this. So if alpha is a is some natural number, then what is x of n log x naught? This is x of log x naught to the power n, which is x naught to the power n. So here when we use x naught to the power n, the meaning of this is x naught produced with itself n times. So this is what motivates the definition of this. We want to just generalize. We want to not just have natural numbers in the exponent. We want to have some arbitrary real numbers. So we want to also talk about things like this. So that is why we have defined it this way, and this behaves very nicely. Basically, you can show things like x naught alpha plus beta is x naught to the alpha, x naught to the beta for all alpha, beta. So the properties of products are taken care of under this definition. So this is very nice way to define general exponents. Alright, so this is all that I wanted to say. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.